Going to finish muscle. We're almost finished with it in your class. And then we are going to start autonomic nervous system. Oh, let me erase the board. I have to redraw it. You have to draw it real time, or else it doesn't stick. Okay, so with muscle adaptation to exercise, which is what we were talking about last time, somebody tell me which type of fibers will preferentially respond if you do what's considered aerobic exercise, meaning high reps, relatively low weight for a decent length of time. What kind of fibers? Slow oxidative. Also some fast oxidative, right? But you might not ever even really recruit your fast glycolytic unless, of course, if you're cycling, you try to go up a hill that's really, really rough to get up, right? Okay. Preferentially, though, if you are trying to get swole, what kind of fibers are you going to be using if you do high weight, low rep? Fast glycolytic. And then, if you have access to some testosterone supplementation, you too could probably really never look like this, but or wouldn't want to. The thing that we need to finish up on that part is just what happens with your muscles as you age. Did we do weak activity last time? Did we do it? Did we do aerobic exercise in here? Okay. Did we talk? Okay, let me just reiterate, even if I did say it before. When you do weak activity over a prolonged period of time, again, what we were saying was that when you're exercising, what you're doing primarily is communicating with your skeletal muscles. And what you're communicating with them, if you go on a 40-mile bike ride, is you're strong enough for the task at hand, but I need a lot of longevity out of you. And they will respond. They do not respond instantaneously, by the way. This is more of a long-term change. They will respond by developing more mitochondria, developing better capillary flow to the muscle, right? And more myoglobin inside the cells. And so it's preferentially the red fibers. And if you train for preferentially red fibers instead of white fibers, then not an individual cell, but a whole muscle might look slightly smaller, right? Not get a significant amount of hypertrophy, but you get tone. But it's like in that situation in which you start working out and you might be heavier, but your pants fit better, right? It's because you get greater tone and the muscle itself is not necessarily getting dramatically bigger because you're not really training for white fibers. Does that make sense to you guys? Okay, so, and then the fact that we talked about last time is that in order to do this activity, you also need to slowly but surely develop those changes in your cardiovascular and respiratory system to support long-term aerobic activity. Good? Okay, so now let's talk about the bad news. And the bad news is what happens as you age. And what happens as you age, it's never good news, really, except you probably get more money, right? That's probably good, but you're going to be squishier. Okay, so maximum force that you can generate in a muscle decreases between 30 and 40% between the ages of 30 and 80. So the maximum tension that your muscle can generate. Now, is that a sentence or is it a predisposition? Meaning, do you know anybody who's 20 years older than you and in better shape? Yeah, there definitely are people, right? Does that happen on accident? Does anybody get accidentally hot in their 40s or 50s? No, you can be accidentally hot when you're 15, 20, 22, right? You don't get accidentally hot in your 40s or 50s. You have to work at it, and gravity is sucking you down, right? Everything's trying to turn to goo. So part of that is just because of your change in your activity patterns. Are these the most active years of your life? They are not. This is usually after you get the job that you wanted that allows you to sit down all the damn time. And then you start getting squishy, right? And you're like, why did I want a job that would make me squishy? So what happens is the fibers tend to decrease in diameter. You don't really lose appreciable numbers of fibers, but you don't need as many myofibrils muscles, right? If you're not using them for generating as much tension, right? So as you break down myofibrils, do you go through the energetically expensive process of replacing all of them? No. So your fibers start to decrease in diameter. And a lot of that loss can be prevented by exercise. So the more active you are, the more of your muscle mass you get to keep. You knew that already. So what happens if you actually lose whole skeletal muscles? Well, you don't lose whole skeletal muscles very often because, remember, they're up to a foot long and they're multinucleated. So even if you damage this end of it, the other end would still potentially be alive, right? So if and when you do damage them, remember that they're amitotic, though, so you don't get any appreciable number of new skeletal muscle fibers. That doesn't happen very often. It could happen with like some kind of crushing wound, or I had a friend that got a brown recluse bite. Yeah, those are nasty. A brown recluse bite, she got it on the back of her leg, and they tried everything. They put her in a hyperbaric chamber, they debrided the tissue. She ended up losing like a big chunk of her hamstrings muscle right back here. And it was gone for good because, of course, the tissue is amitotic and she had just lost all of that tensile strength. So it's because the brown recluse venom causes tissue necrosis, right? It kills off the tissue ahead of itself. Okay, so now, just for comparison's sake, we're going to talk about smooth muscle tissue just briefly. We're not going to talk about cardiac muscle tissue because we actually are doing cardiac muscle tissue right after your test, so we'll just leave that for then. Okay, so I just want to compare and contrast skeletal muscle to smooth muscle tissue. What does it have in common anatomically? What does it have in common physiologically? What is different? First off, you already know that smooth muscle tissue is, of course, non-striated, right? And under involuntary control. Skeletal muscle, most of it maps to your cerebral cortex, so you have the capacity for conscious control of skeletal muscle activity. Smooth muscle activity does not map to your cerebral cortex, so you don't really have any conscious control of smooth muscle or voluntary control. So it's controlled by the autonomic nervous system, which is what we're about to do right after this. And it contains, the cells do contain actin and myosin, and they have a similar contraction mechanism, but since the actin and myosin don't line up, it doesn't look striated. So let me show you this. This figure is from the anatomy textbook, not the physiology textbook. But please note, look, doesn't this look like actin and myosin? Yeah? I mean, it might not end in a Z line, and it doesn't, right? But it actually has a similar cross-bridge cycling pattern, uses ATP in kind of a similar way. But please note that if the myosin doesn't line up, you don't get striations, right? And this myosin is going at all angles to one another. Does that make sense? So there's no striations, even though there's a lot in common with the contraction mechanism. But there are some differences as well. You know that the cells are small, they're uninucleated, they're spindle-shaped. I don't know why they continue to put spindles in textbooks, because it's not like any of you guys have ever seen a spindle. They look like an eyeball. You've seen an eyeball, though, right? Okay. They look like an eyeball. They are eyeball-shaped. I don't think I've ever seen a spindle, right? Like a spindle. Maybe in a Disney movie. What? Yeah. Was it Cinderella? Was that the spindle? That's Sleeping Beauty. Yeah, Sleeping Beauty.
Just so y'all know, I know my Disney.
Okay, so the cells are uninucleated. One of the other important things about smooth muscle, unlike skeletal muscle, is that most smooth muscle tissue can go through mitosis if it gets damaged. And it maintains the capacity to go through cell division into adulthood. That means if someone had, for instance, an emergency cesarean, right, would the smooth muscle in the wall of the uterus potentially regenerate? Yes. Does it every time? No, but it potentially does. Okay, and then how about its cross-bridge cycling? It has a slower rate of cross-bridge cycling, which of course means it uses less energy, right? It's not really an emergency response tissue, so the rate of cross-bridge cycling doesn't really have to be very fast. In addition, the calcium pumps on the SR are slow, so every single time the calcium is released, it stays out there for longer, right? So you get a longer contraction for each calcium release. So you also don't store as much calcium because you don't need it. You like release it and just leave it there. Okay, it has a similar strength of contraction if the cells were the same length, but it can maintain a sustained contraction for a long period of time. And the other interesting thing about smooth muscle is that you guys know, like, the mechanics of skeletal muscle says that skeletal muscle is going to contract better from here than it is from here, right? And you're going to be able to generate more tension strength from here than you are from here, right? Well, smooth muscle, interestingly, can contract really well when you stretch it 2 to 8 times its length, which is pretty damn important, because when does your uterus contract the best? When there's a baby in there. When does your stomach contract the best? After Thanksgiving dinner, when you like put in all the mashed potatoes you possibly could, right, at that particular moment. That makes sense? So it contracts well when it's stretched. Okay, and then this is going to be important today too. Skeletal muscle only has a gas pedal on it. You can either stimulate it or you can leave it alone, but it does not have a brake, okay? But smooth muscle, in most places, it has the ability to actively excite or actively inhibit the smooth muscle. Yes? Okay, so it's got a gas pedal and a brake on it. So keep that in mind. It's going to be important today. The other thing about smooth muscle is that whereas skeletal muscle really is only controlled by the nervous system, I mean, in your body, you can be, electrocuted, but in your body, if the nervous system doesn't tell skeletal muscle what to do, it doesn't do anything, right? Smooth muscle can take a lot of different kinds of input to decide whether to contract. First off, it has spontaneous electrical activity. It goes through a pacemaker potential, and your smooth muscle just spontaneously contracts and starts a peristaltic wave of contraction. But then, as I mentioned, the autonomic nervous system can also speed it up or slow it down. But then smooth muscle can also be hormonally triggered to contract. That shouldn't be surprising, right? That's what childbirth is about, right? Hormonal triggers for contraction, yes? But not just childbirth, because we've all experienced it. Has anybody ever, you don't have to raise your personal hand, but you can think in your personal head about if any of you guys have ever gotten so damn stressed out that you get the squirts? Oh yeah, right? I am so damn stressed out that I have pooped like 72 times, right? Or you can get so damn stressed out that you don't poop at all for like 3 days, right? That's like the vacation stress poop, right? You're like, I'm in a different country, the toilet confuses me, I'm literally not going to poop until I get back in the United States. Go ahead.
Can that kind of have the effect like with anesthesia? Because like I
Yes.
had anesthesia before and like I could not poop for like 5 days.
Yes. And that alone makes you need some anesthesia. You're like, I literally want to be knocked out until I poop. So yes, anesthesia does it as well. Okay. So, and then paracrine agents can cause smooth muscle to contract and stretch alone. Like if your stomach gets full enough, it'll just start to contract. It'll be like, I'm too full, let's contract. Okay, so last thing is just to separate 2 different categories of smooth muscle tissue. You ready? Not all smooth muscle tissue is the same. There are 2 different categories. And this confuses people. And note to self, I'm going to tell you guys this. You know the most likely questions that will be missed in any set of notes are the ones on the back page. Okay? People flip, done with that one. They don't even look at the back page. I'm telling you this because this question is really commonly missed, even though it's easy, super duper easy. You ready? Okay. 2 different categories of smooth muscle. One of them, look, has gap junctions between, right? And they all behave as a single unit. That's why it's called single unit smooth muscle. Because although these look weird, these are actually the axon terminals for the autonomic nervous system. If you stimulate these are all going to contract in a wave, like in the wall of the uterus or in the wall of the digestive tract, to cause peristaltic contraction, right? So these behave like a single unit, but not everywhere do you actually want for all of the cells to do the same thing. You can also have cells that behave like multiple units. Do you see each of these has the capacity to be talked to by the nervous system? That's called multi-unit smooth muscle. It's when you want to be able to tightly control something, even if it's controlled by smooth muscle. For instance, if I want to constrict an arteriole to slow down blood to an area, do I want to constrict the whole blasted thing? No, I just want to use a cuff, right? So I want to be able to control cells individually. Or the cells that are controlling the diameter of my pupil. Do I want to use them all or none of them? No, I want to be able to make minor changes, right, to the diameter of my pupil. Also, the erector pili muscles. So these guys are rare examples of smooth muscle. They're not the ones that people are usually talking about when they say pacemaker activity and peristalsis and all that kind of stuff, but they're important too. Okay, so single unit smooth muscle behaves like a single unit. It's also called visceral smooth muscle because it's in your guts. Multi-unit smooth muscle, individual units. Yes? Got it? Okay, so that's the last of that set of notes, and now we are going to do autonomic and somatic motor nervous systems. You ready? Okay, so we're going to start with that should have been Roman numeral 2. We're going to start with this Roman numeral, which is the second Roman numeral 1. Okay, so let me give you a heads up. Okay, the only thing difficult about this set of notes is the terminology. So you will see that the physiology is not very difficult, but there are a jillion words and they all have like too damn many syllables. Parasympathetic, preganglionic, acetylcholine, postganglionic acetylcholine in the autonomic branch of the parasympathetic nervous system, right? So your objective, if you didn't already do it in anatomy, is to make sure that that terminology doesn't throw you so that you don't understand a simple question. Does that make sense to you? Okay, and so first, let's just acknowledge which part of the nervous system we're going to be talking about here. Actually, we've already been talking about the somatic nervous system, right? Because we've been dealing with stimulating skeletal muscle. What this set of notes is going to do is take what you learned in the somatic nervous system and compare it to the autonomic nervous system, which is a little bit more complicated, but you can use it as comparison contrast. It's not terrible. So basically, the nervous system does three things, right? Information in, which is sensation, information process, which is integration, and information out, which is response or motor activity. We're going to be focusing on the third part, information out, which is motor activity. Okay? Got it? Okay, so let's see how you guys do on these questions. So characteristics of neurons, before we go any further. Neurons have two special characteristics. One of them is that neurons can take almost any kind of stimulus, a light, a chemical, pressure, whatever, pain, and convert it into an electrical stimulus that they can send 250 miles an hour, an action potential. So question, what cell membrane structure allows them to take any kind of input and convert it into an electrical stimulus? What is it? What is it on the cell membrane that allows them to... The receptors are on this end, and a lot of cells have receptors, but cells don't have the thing that can convert that into an electrical stimulus. It's a kind of channel. Voltage-gated. Yes, voltage-gated ion channels is what they have. Okay, last question, and then I'll stop torturing you with cell stuff. Ready? Okay. By the way, I updated the notes. If you didn't get the updated ones, yours will be slightly different, and they won't have the cool picture in them. Okay, so neurons also have this characteristic. They can transmit an action potential to another cell. Not directly, but they can force another cell to have an action potential because of something that only they release, which is what? Yeah, neurotransmitters. Okay, so here's what we're going to do just to make sure that you guys understand the big picture before we go any further. You had this picture in your quiz, so this won't be too hard, but I want to make sure that we're all on the same page as far as terminology, because actually 11 of you didn't do your quiz, which is, I don't even understand you. I mean, didn't even open it, didn't even try to do it. So, okay, so here's the deal. Same thing that I do in anatomy, just to make sure we get the terminology down. Okay, we're going to primarily be over here today. Yes, CNS, PNS. So one-way or two-way communication between the CNS or PNS? Two-way. Yeah. So I'll draw two arrows. Which of these arrows, top or bottom, gets the afferent word? Top. Yeah, this is afferent. Yeah. And then this one gets efferent. Okay. And what the CNS does is integration. Basically take sensory information, figure out what the hell to do about it, send it back out as motor information. Okay, so we're going to be in the PNS today, and specifically we're going to be in one branch of the PNS. But let's just go ahead and acknowledge that the other branch exists. So the PNS is divided into the Afferent Division and the Efferent Division. And let me just acknowledge that I'm saying those wrong for effect. It's actually afferent and efferent, but if you are teaching, they sound the same. So I'm just Texas twanginize them for you, Okay, so afferent and efferent. So the afferent nervous system is sensory, okay? And basically what it's going to do is take information from sensory receptors, right, and send it up. But we're not concerned about that part right now. We're going to be concerned about this part, which is the efferent nervous system, also called what? Motor. Efferent or motor, okay? So let's acknowledge some stuff that we already know, that we've been working on already. The efferent nervous system has two further subdivisions. It's got the somatic motor, and the somatic motor goes to a certain effector. What is the effector for the somatic motor division?
Skeletal muscle.
Yes, so skeletal muscle. Effector. Okay, so there's only a gas pedal hooked up to that, right? There are not two hookups to the skeletal muscle, just one. And either you stimulate it and get it closer to a contraction, or you leave it the heck alone, okay? But when we get to the efferent motor division, we will see that the other division is called the autonomic motor. And the autonomic motor goes to three different effectors. What are they, guys? Smooth.
Glands.
Yep.
Cardiac.
Glands. And cardiac. Okay. Now this is going to be the important part. The autonomic motor has a further subdivision. Okay, and you've learned this before, but it's the sympathetic and parasympathetic. Now, this is two different hookups to the same organ. So we could go to each of these organs and we would have what's called dual innervation to an organ. Okay, so you guys know sympathetic and parasympathetic already, right? You associate the sympathetic branch of the autonomic nervous system with what functionality? Fight or flight, exercise, right? Fight or flight and exercise. And the parasympathetic is? Rest and digest, or feed or breed. The way that I learned it is that the autonomic motor division does the 4 F's. Fight, flight, feed, and breed. Yes? Yeah. Okay. All right, so here's what I want you to understand before we go any further, and then we will reinforce this, add some neurotransmitters, add some examples. Okay, so what I mean is I have dual innervation of my heart. Okay, everybody can picture where the heart is, so we can use that one as an example. So what's going on with you guys right now, because you're just sitting, you don't have a quiz, right? Your test isn't until next time, there's nobody in here trying to kill you, right? What happens is my heart has a gas pedal and a brake, yeah? And so right now what you are doing is you are actively inhibiting what your heart could do. You are putting the brakes on. Does that make sense? Okay. And which branch of the autonomic nervous system is doing that for you? Parasympathetic is doing that for you. Does that make sense? Okay. But now let's imagine that a tiger walks into the room. And tigers are really freaking big. Have you seen how big tigers are? They're amazing. Okay. So a tiger walks in the room because the door is open. All right. That's like tiger friendly. Okay. So tiger walks into the room. Then what's going to happen is we have entirely different resource allocation needs, right? But let's just focus on the heart. So what is going to be needed at the heart? So what we are going to have to do in that situation is we are going to have to take first our foot off the gas, reduce parasympathetic stimulation, but that alone is not going to get us enough to get away from a tiger, right? So then what we're going to have to do is put our foot, did I say off the gas? I meant off the brake, put our foot on the gas. Does that make sense? Okay, that's the sympathetic nervous system. So it's going to increase sympathetic stimulation, which will do what to your heart rate? Okay, now, everybody understands the heart, but what happens is people make this really common mistake of assuming that what I am saying, or what anyone is saying, is that the sympathetic increases the activity of all tissues. It does not, because you have a finite amount of resources, right? You've got a finite amount of oxygen and glucose and nutrients and even blood. So now I want you to think about a different organ in the same scenarios, right? This different organ in the same scenario also has dual innervation. I want you to imagine the uterus, right? What tissue in the uterus are we going to be controlling right now? Smooth muscle, okay? So your uterus might be really busy right now, You might be aware of it, you might be not. It might be making an endometrium, it might be contracting, it might just be sitting there being a jerk and making your life miserable. Who the hell knows what it's doing? So whatever it's doing, right now, the parasympathetic nervous system is doing what to the uterus because it can afford to? Increase or decrease the activity of the uterus? Increase, yes. That make sense? Okay. Whatever its uterus job is right now, it's on the way of doing it, right? But then a tiger walks into the room, yes? And what happens to the uterus? Okay, so I had the gas on the uterus, right? Which was the which branch? Parasympathetic was the gas for the uterus, because it ain't gas and brakes for all things, right? Parasympathetic was increasing the activity of the uterus, right? And now I take my foot off the gas, but I've got to save more resources than that, so what do I do with the sympathetic nervous system? I inhibit it further. Yes? I inhibit it further, right, to save resources. Does that make sense to you guys? Mm-hmm. So the thing that I want to reinforce is do not get into the habit of thinking that the sympathetic nervous system increases the activity of all tissues, because you would use up your resources instantaneously, and then the tiger would eat you, right? So we want to get away from the tiger. Okay, so here's what we are going to do. We are going to briefly, let's just reinforce the afferent division of the nervous system. The afferent division of the nervous system is sensory receptors to the CNS ultimately, but you're not actually aware of all sensations. You're only aware of sensations that end up in your cerebral cortex, and that's not very many of them. You're monitoring your own heart rate and uterine contraction right now with sensation, but you're not aware of it, right? So only if it goes to the cerebral cortex are you actually ever aware of it. Okay, the efferent division is subdivided into the somatic motor and the autonomic motor. The somatic division you already know, but I want to reinforce it so that I can use it for comparison contrast. So the somatic division is wired up mostly to the cerebral cortex. This is not the cerebral cortex, of course. But, okay, so the somatic motor division of the efferent nervous system is your voluntary nervous system. And you are usually in voluntary control of much of your skeletal muscle, not all of it. And that's because it maps to the cerebral cortex. Does anybody remember which portion of the cerebral cortex most of your skeletal muscle control maps to? Do you remember? Precentral. Good job. Yes, touchy-feely. Precentral gyrus is touching, postcentral gyrus is feeling. Touchy-feely, touchy-feely, touchy-feely. Precentral gyrus of the frontal lobe of your cerebral cortex. That's where most of it goes. Okay, so you are in voluntary control of like doing this and doing this and doing this, right? All of that to there, most of it to there. Okay, so now let's talk about the anatomical route. So the anatomical route to controlling skeletal muscle starts in gray matter somewhere. It's not all there, but some of it is. This one's actually showing you a little bit simpler one, with this one's coming from the gray matter response cord. So here's what I want to do. I want to make it so that we can use this as a comparison contrast. So here we go. We are going to do, the entire thing is going to be efferent nervous system, okay? And we're going to divide it into SNS, which is somatic, and ANS, which is autonomic, right? And what we're going to keep track of is where things are and ultimately the effect. So we're going to start in the CNS. We're going to end up at an effector. And we're going to look at the anatomical route and the neurotransmitters that are released, right? Okay. So the CNS, what goes through the PNS, what the effector is, and the impact or effect, basically excitatory or inhibitory. This one's really easy. Okay. Okay. So the anatomical route for this one is super duper simple, and that is neuron cell body is in the CNS. Where is it? Somewhere in the gray matter of the CNS. The one that actually controls here is controlled from my cerebral cortex, but the neuron cell body that's doing the controlling is actually in the cervical region of my spinal cord. Does that make sense? The cerebral cortex tells it what to do, but it's in the cervical region. Or the one that's controlling my little toe right here, contracting, is in the lumbar region of my spinal cord, but still in the gray matter, still in the CNS, okay? What is the effector for the somatic nervous system? Yeah, skeletal muscle. So you guys can even recognize a bad picture of skeletal muscle, right? Okay. So this is a really, really simple anatomy. The neuron cell body is in the central nervous system. The only thing that goes through the peripheral nervous system is an axon. That's it. It doesn't release any neurotransmitters along the way at all until it gets to the effector. So there's one neurotransmitter release opportunity, and it always has the effect that you know. So you guys tell me, what neurotransmitter is always released here? Acetylcholine. And what is the effect? Excitatory, inhibitory, or you have no idea? That's always excitatory. That doesn't mean you're always going to get a contraction, but it means you're always going the right way. Okay? All right. So let's use that for comparison contrast and then make sure that you actually can do the next part. So the anatomical route from the CNS to the skeletal muscle is simple. Somatic motor neuron cell body is in the CNS. The axon goes through a nerve, cranial nerve, spinal nerve, branches of them, whichever, to synapse at a neuromuscular junction. No ganglia, only one synapse. So let's make sure you guys can do this. Should be super easy. It releases acetylcholine. The effect is always excitatory. The mechanism of excitation is generally to open what kind of ion channels? Sodium channels, yes. They're not voltage gated until you hit threshold. They're acetylcholine gated at first, and then you hit threshold. Sodium channels, and cause what kind of polarization? Depolarization. And of course, these synapses would be called what ergic? Cholinergic. Okay, so now let's back to that first question of the quiz that you guys did. That for some reason was a quiz question that people had trouble with. And I think it's because you run into a lot of words and you're like, oh my God, words are hard. No, words are not hard. So neuromuscular junctions for skeletal muscle are always excitatory, cholinergic. Yes, yeah. And as a matter of fact, they're ionotropic, so they're fast excitatory, cholinergic. Okay, so now let's use that for comparison contrast because this one's harder. So let's build a little bit of information and then we'll fill that in. Okay. The autonomic nervous system is usually called the involuntary nervous system or the visceral motor. And it's autonomic as in autonomous, right? As in something that runs on its own without your control. Yes? So, and of course the effectors that they control are cardiac muscle, smooth muscle, and glands. So I will acknowledge that the terminology associated with the autonomic nervous system is ridiculously obscure. It doesn't really relate very much to anything else you've ever learned, and it's a little annoying to try to learn. So why do people try to teach you the autonomic nervous system at all? Well, if you control cardiac muscle, smooth muscle, and glands, you are in control of most of the body systems that will end up making you seek medical care, right? Cardiovascular system, both cardiac muscle and, of course, the smooth muscle that controls vasoconstriction and vasodilation. Respiratory function, now, admittedly, it's the somatic nervous system that controls the diaphragm, but it's the autonomic nervous system that controls the diameter of the bronchioles, right, on the way to the lungs. Digestive function is all wiggling and squirting. It's all smooth muscle and glandular function, right? Urinary function, it's blood pressure that determines urinary volume, and then there's a bunch of glandular secretions that are involved in it as well. And reproductive function, if you're doing it right, it's all wiggling and squirting. That's all it is, man. Smooth muscle and glandular function, right? So you need to know how it's wired up. So when it goes bad, you might have a better idea of how it should have worked. So what we are going to talk about is the dual innervation of the autonomic nervous system, and then sort of understand sympathetic and parasympathetic. Okay, so dual innervation, that concept is really important. So let's look. Have you guys seen this picture before? It looks so outrageously complicated, but it's really, really not. Okay, what this is showing you is all of these guys in the middle are autonomic effector organs, right? They will have cardiac muscle, smooth muscle, or glands, or a combination of them in them. And they have dual innervation, the vast majority of them do, from the parasympathetic nervous system and the sympathetic nervous system. You with me? Okay, so let me just reinforce some anatomy. Did any of you guys not do autonomic nervous system and anatomy? Anybody not do it? Oh, you haven't done it yet. Yeah, you haven't done it yet. Okay, so here's what I want to tell you. I want to put together a little bit of the anatomy story so that the physiology will not be as completely unrelated to anything you've ever learned. So the anatomy story goes like this. So the parasympathetic nervous system goes to your autonomic effector organs. Picture the heart, because everybody knows where it is, right? From 4 cranial nerves, and then nothing at all. It doesn't go to your heart from here, but no effector organs until you get down to the sacral region of the spinal cord. So do you see that in the purple? All the parasympathetic innervation is from 4 cranial nerves and then nothing until you get down to the sacral region of the spinal cord. So do you see with just that snapshot, you can tell, oh, that's parasympathetic innervation, just because of where the wiring is coming from. Okay? Okay. Now, the sympathetic innervation does not come from those regions at all. It comes primarily from the thoracic region of the spinal cord, a little bit lumbar, right? So here's what I want to tell you. What I want to reinforce is, based on what we talked about before, right now, before there's a tiger in the room, I want to figure out what the hell is going on with your heart and how is the neurotransmitter chilling out your heart right now. So what is happening right now with your heart is the brakes are coming through, watch, cranial nerve number 10, which is vagus nerve, and it is going to go down to your heart and say, chill the heck out, ain't no tiger in the room, right? So that's the anatomical route coming down. You've got 2 vagus nerves actually coming down. That makes sense? Okay. Tiger walks into the room. What you do is stop stimulating the vagus nerve, which takes your foot off the brake. Yes. Okay. And then freaking tiger, take your foot off the brake is not enough. So what we do is we send a stimulus down to the thoracic region of the spinal cord, up to the heart. Yeah? That's what it's doing. So do you think that you could recognize the difference between the sympathetic and parasympathetic on a simple diagram? You certainly should be able to. Thoracic and lumbar region is sympathetic, and cranial and sacral is parasympathetic. Okay, so that's the anatomical route, but now we've got to add some complexity to it. So the sympathetic division is going to activate fight or flight and exercise responses of those 3 tissues. The parasympathetic division is going to activate feed or breed responses of cardiac muscle, smooth muscle, and glands. Now, these 2 kind of act as antagonists to one another. Generally, not exclusively, but generally, you don't have to memorize what both of them do, because if you know that the sympathetic increases heart rate, what does the parasympathetic do? Decreases it. If you know that the parasympathetic nervous system increases smooth muscle contraction in the digestive tract, then what does the sympathetic do? Decreases it. And that's right almost all the time. The exceptions are memorable enough that you'll be able to remember them. Okay, so they act in opposition to one another. In order to figure out which one does what, you can memorize all of them. Don't memorize. Here are all the tables from your textbook that show you sympathetic and parasympathetic functions. And that was just a cartoon. And there's SpongeBob. Or you can think resource allocation. And if you think resource allocation, it will get you the vast majority of the way there. And resource allocation is just, could I afford to do this if a tiger was about to eat me or someone was about to kill me? If not, then the sympathetic nervous system is probably not going to turn on that activity. Does that make sense? And we'll do the resource allocation practice a little bit later. Okay, so let's talk about the anatomical route from the CNS to the effector and the autonomic nervous system. So we will draw cardiac muscle. Okay, it's one of the possible effectors. It's the one that you can recognize best from a bad picture. And then, so we're going to draw this simply, and then we're going to have to break it out into sympathetic and parasympathetic. But basically, first, it starts out slightly more complicated, even though the neuron cell body is in the central nervous system. This neuron does not go all the way to the effector. This neuron will make a pit stop on the way with another neuron that will then go to the effector. Okay? This neuron is in a blob of neurons outside of the central nervous system, in the peripheral nervous system. What do you call a blob of neurons in the PNS? Ganglion. So this is specifically an autonomic ganglion. Got it? Okay, so what we will see in just a minute is now we're going to have to look at two different neurotransmitter release activities. Okay, now, does it surprise you at all that the sympathetic and the parasympathetic nervous system cannot release the same neurotransmitter at the effector and cause two different responses? They're going to have to release two different neurotransmitters to cause two different responses on the same cell. Yes? Okay. So this is just your basic anatomy. And then what we're going to have to do is we're going to have to blow it up and look at the difference between the sympathetic and the parasympathetic. Okay? So let's just make sure that the words will make sense to you. So the ANS, anatomical route from the CNS to the effector. The neuron 1 is in the gray matter of the brain or the spinal cord. Please note that you have enough anatomical and physiological knowledge to know that the information going through these two is going that direction, right? Okay? So you could term one of these the preganglionic neuron and the other one the postganglionic. Yes? Which one's preganglionic? This one, yeah. Okay, preganglionic. Preganglionic neuron, axon, whatever you want to call it. Postganglionic. Okay? So the cell body of neuron 1, preganglionic, is in the CNS. The cell body of neuron 2 is in the ganglion and proceeds after as a postganglionic neuron. So basically we have a 2-neuron chain instead of a 1-neuron chain on the way to the effector, with one exception. You ready for the exception? And I will reiterate this a little bit later too. The one exception to the 2-neuron chain on the way to the effector is the adrenal medulla. The adrenal medulla has something slightly different. So here's the first neuron, the preganglionic neuron, yes? And it releases its neurotransmitter. We'll identify that neurotransmitter in a second. But please note that this second neuron has lost its axon. It's an anaxonic neuron. They call it a chromaffin cell. Okay, so when it releases its neurotransmitter-like substance, it just releases it into a really rich capillary bed, and it gets picked up by the bloodstream. And so it behaves more like a what than a like a hormone. This one you actually know, even though you might not know you know it. It actually releases the hormone called epinephrine or adrenaline into the bloodstream in response to what? Sympathetic or parasympathetic stimulation? Sympathetic. Okay, so this is the only real exception to the 2-neuron chain, but it's only kind of an exception, right? Because it just evolved without an axon and dumped it into the bloodstream. So we'll talk about the functionality and why that's good in just a minute. Okay, so now we just have to add in some more details. So what we're going to do now is separate this, the autonomic nervous system, into sympathetic and parasympathetic, and then add in our neurotransmitters. So we're going to do the same thing that we did before. We're going to separate it into sympathetic and parasympathetic. Okay? And we'll do CNS, PNS, effector, response impact, whatever you want to call it. Okay, so this is where it gets a little hairy, but it clarifies if you just give it a minute. Like, it gets all confusing and then it'll clarify. Okay, so the preganglionic neurons are both in the CNS, but let's just acknowledge something. You ready? I'm not going to make you memorize this anatomy. I just want to show you something. Okay, if we're talking about the heart, have you ever heard that the medulla oblongata controls heart rate? You should have. Okay? Why? The preganglionic neuron to control heart rate is in the medulla oblongata, right there. Okay? Now, so it actually is responsible for slowing down heart rate through the vagus nerve. So that first one is there. Okay? The first one for the sympathetic nervous system is usually going to be in the thoracic region or sometimes the lumbar region of the spinal cord, but still in the CNS, right? So the first neuron cell body is in the CNS. Okay, so the preganglionic neurons of both sympathetic and parasympathetic are going to synapse onto a ganglion. So what we are going to do is sympathetic has short preganglionic. Parasympathetic has long preganglionic. And they're going to synapse. Okay? And then the second one will go to the effector. They're going to share an effector. Dual innervation. Okay? The second one is going to go to the effector as well. Okay. So here's where it's going to get all hairy and then it'll clarify. It gets easy after a minute. Okay. So the preganglionic neurons of both divisions, sympathetic and parasympathetic, will release acetylcholine. So what I'm saying is acetylcholine will be released here and will be released there. Got it? Okay. And here is what is also true. When acetylcholine is released here, it's always excitatory to this neuron. I'm not telling you what it does here. I'm telling you that the signal does not stop halfway through. Go ahead.
So I'm kind of listening to you. Acetylcholine is always excitatory.
No.
Not always?
No.
Okay.
There's an exception.
There's one
Okay.
exception?
Mm-hmm. There will be one exception in this whole story in which acetylcholine can do whatever the hell it wants. Okay? You ready? Okay. However, what Cody just said was, it's Cody, right? Or Colby? Which one? Charles. Whatever, Charles.
Just call me Charles.
You've been Charles for a year now. Now I'm trying to change, and you
Don't
literally
change.
Okay, I'm not going to change.
Just
Charles,
keep
you're in
Charles.
trouble. Take out the garbage. Okay, you ready? So, I am going to show you a pattern that he started to recognize, and that is that this entire thing is the efferent nervous system. Yes, the entire thing. Okay. Do you see that in the entire efferent nervous system, acetylcholine is released first, even if there's not a second? Yes? Do you see that? Acetylcholine? Yes? Okay. And when released first, it is always excitatory, because it's excitatory there. It's excitatory here.
So when it's released first?
First, yes.
So the first initial...
The initial release of acetylcholine in the entire efferent nervous system is excitatory. Yes? Okay. So it's going to be excitatory here and excitatory here. Yes? Okay. So let's go back just a little bit more and make sure we fill in a little bit more detail. Preganglionic neurons of both sympathetic and parasympathetic nervous system are going to release acetylcholine. It's going to bind to nicotinic cholinergic receptors. So it's going to cause a fast excitatory response. And the mechanism is what you think it does. It opens what kind of channels?
Sodium?
Sodium. It's going to be sodium. And cause what kind of polarization? Depolarization. These synapses will be what ergic? Cholinergic. Okay. Now keep that in mind, and let's do that next question. Okay. Postganglionic neurons. Okay. Postganglionic neurons, they can't release the same neurotransmitter at the same tissue and cause two different things. Okay. So let's separate them out. Postganglionic neurons in the parasympathetic nervous system right here will release acetylcholine again. But I want you to think about this for just a second. Is acetylcholine excitatory to everything? Is it inhibitory to everything? What does it depend on? It depends on the receptors that it binds to. So let's ask ourselves that question with cardiac muscle. Ready? Start. You're going to hear one of the super duper wordy questions that are actually relatively simple. Just lots of vocabulary. Okay. What is the effect of parasympathetic postganglionic acetylcholine on cardiac muscle? Excitation or inhibition? Inhibition. Because what I'm really, really asking is, what does the parasympathetic nervous system do to cardiac muscle? Inhibits it. And now I'm asking you, do you know the neurotransmitter that is used in the process? Does that make sense? Okay. Now let's ask a different question though. What is the effect of parasympathetic postganglionic acetylcholine on the smooth muscle of the uterus? Excitation. Yes. That makes sense? So it depends on the receptors that it binds to. So that's why I couldn't say yes to your answer. Because acetylcholine, once it gets to the effector, has to deal with different receptors. Yes? Different receptors in different places. Got it? Okay. So we know
But everything before. So
everything before this final effector So again, I'll reiterate what I said, and it's true. In the entire efferent nervous system, acetylcholine is released first, and when acetylcholine is released first, it's always excitatory. Okay? This one just doesn't have a second, so that's just the end of the story. Yeah? Okay? All right, so logic question. Make sure this makes sense to you, okay? I hope it does, because that will mean that this isn't just a whole bunch of word salad. Do you understand that I absolutely positively know that this cannot be acetylcholine? Toby understands.
Yeah, because you can't have the same neurotransmitter and do the
Yeah,
same thing.
So what would happen if the sympathetic nervous system also released acetylcholine on the heart?
Inhibit.
Yeah, you could not cause two different responses, right? That removes the benefit of dual innervation, right? That makes sense? Okay, so you might not know what it releases, but it ain't acetylcholine, right? And what it is primarily norepinephrine, also called noradrenaline, and a little bit of epinephrine. As far as the neurotransmitter most likely to be released is norepinephrine. As a hormone, it's more likely to be epinephrine. They interact with most of the same receptors. Okay? Norepinephrine. Okay, so postganglionic neurons in the sympathetic division of the ANS release norepinephrine or epinephrine. This synapse would be called whatergic? Adrenergic, yes. The effects of either postganglionic neurotransmitter can be excitatory, they can be inhibitory, because it doesn't really depend on the neurotransmitter, it depends on the receptor. Exactly. Okay, so let's do the damn questions again. Freaking wordy ass questions, Melanie. Okay, I don't like the terminology associated with this either, but you gotta be able to do it. Ready? What is the effect of, I'm gonna give you guys like 3 different questions. Ready? What is the effect of parasympathetic preganglionic acetylcholine? Yeah, excitation, right? I don't even need to finish the question, right? Because that's the place that it acts, the ganglion, right? Okay. What is the effect of sympathetic postganglionic norepinephrine on cardiac muscle? Excitatory. What is the effect of sympathetic postganglionic norepinephrine on the smooth muscle of the digestive tract? Inhibitory. Got it? Right? So you know the ends, right? And you just have to make sure that you understand the neurotransmitters that are in the middle. Go ahead.
So is the sympathetic system always going to be acetylcholine at the ganglion and then norepi or epi at the...
Yes.
Okay.
Uh-huh.
So norepinephrine is...
So it's just depending on if that's something you want to turn on or off in
Yeah.
that system.
It's just, so you use the same... You use the same signal, you just use different receptors for the same signal, right? You always use norepinephrine, epinephrine, but you can have an excitatory receptor or an inhibitory receptor in different tissues. I'm going to show you an example of that in just a minute. Go ahead.
Kind of answering my own question, but...
Well, it's probably really eloquent, and everybody needs to hear how smart you are, so go ahead.
The acetylcholine is more abundant than norepinephrine, correct?
It's more commonly used
More
in the peripheral
commonly
nervous system,
used.
yes.
Okay, so that makes sense why
Yes.
it'd be the parasympathetic, because
Okay.
parasympathetics, you use that more than...
You actually do use parasympathetic more. You don't just, I mean, FYI, we're telling a little bit of a fib about the sympathetic nervous system. We say fight or flight or exercise, but you actually tweak it all the time during the day, right? You get up and you like go to the car and you like tweak it, right? And you're like, and you turn it back off. But the parasympathetic is often used more frequently. The sympathetic is not only for emergency situations. They just teach the extremes so that you can start to understand it. Does that make sense? Okay, so let's acknowledge something that we actually have time to in this class, which is kind of interesting. Oh my gosh, you never asked questions. I'm so excited. Yay!
So I'm just curious, so the parasympathetic, when the acetylcholine is released on the cardiac muscle, it's not sodium, is it? Or
Yeah, it doesn't use sodium. I think that was a chloride channel, actually. Yeah, it uses a chloride channel, yeah. But you don't have to memorize all of the receptor activities. Okay, so 2 things. First off, and this is fine if you don't understand this, but I want to try to put it together with it, because I've had students ask this before, and they sit at home and they like try to figure it out and flip it around. So This is always happening in your peripheral nervous system when a tiger walks into the room. Or when you see a person you're really attracted to. It doesn't even have to be bad excitation. It can just be like, oh, this is stressful. Bad job interview, hot girl, tiger. All the same thing, really. So, he's like, I got it, yeah. Okay, so we're talking about what the peripheral nervous system does on those fight, flight, exercise, stress situations. Let's go ahead and acknowledge that we also know some of what the central nervous system does, right? What is the central nervous system doing in situations in which a tiger is in the room? Let's go to the extreme. You actually know some of this because we learned it in the synapse notes. What's the central nervous system doing? Okay, so I know it's controlling this, but what's going on in your brain? What kinds of neurotransmitters are involved in that situation? Do you remember? You want to feel 10 foot tall bulletproof? Yes, endorphins and enkephalins, those are being released. Also norepinephrine, which is your up, right? Neurotransmitter. Does that make sense? That makes sense? And once you get a little further into it, if you survive it, you'll release dopamine to say you are the strongest tiger beater in the history of tiger beaters and try it again next time. That makes sense? So this is working parallel and complementary to the CNS stuff, but this is all PNS stuff. Does that make sense to you guys? Okay. There's a lot of neurotransmitter activity happening. I almost fell onto my face. Yeah, sympathetic. Oh, my sympathetic nervous system goes crazy. I wonder what my heart rate is right now. Let's see. It's 102 when I'm teaching. It's like really, really high when I'm teaching. Because if you guys think I'm lazy, it's because you're a jackass. You know what you're talking about. Okay. You ready? So let's make sure that you guys can fill this in. Okay? So I left some blanks on here for you, and you have it basically for you. I don't care if you know about myelination versus not myelination in phys. In anatomy, it's interesting, but there are more important things to spend time on. So I left you some blanks. I left you this blank and this one and that one and that one. So let's fill them in. Okay, you ready? Okay, so first thing is the entire thing is the what nervous system? The entire part that controls skeletal muscle is the what? Somatic. That's the somatic nervous system. Okay, so let's fill in the rest of the somatic nervous system. The somatic nervous system releases what neurotransmitter at the effector? Acetylcholine, and the effect is excitation or inhibition? Excitation. You got it, right? Okay. All right. And then this branch, which includes the parasympathetic and its friend that we don't know the name of, this entire branch is called the what? This was somatic. This is autonomic. Okay. And its two branches are the parasympathetic and the sympathetic. Okay, you ready? Now, the sympathetic nervous system usually has a 2-neuron chain. We've got the little exception right here. Okay. The first neuron is going to release what? Acetylcholine. Both places, right? But just in case you couldn't remember, I left that one in for you. Okay. And then you are going to release what neurotransmitter at the effector with the sympathetic nervous system? Primarily norepinephrine as a neurotransmitter, a little bit of epinephrine, okay? And here are your effector organs, cardiac muscle, smooth muscle, and glands. The effect can either be excitation or inhibition depending on the receptor, right? And you use resource allocation to figure that out, and we're about to practice that in just a second. And then the very, very last thing is the parasympathetic nervous system releases acetylcholine here. And what does it release here? Acetylcholine again. That make sense? Okay. Okay. So now we get to do the fun part, the interesting part, where we actually start to get to the point that we can do pretty solid predictions of what the sympathetic and the parasympathetic are going to do. We also want to get rid of the misconception that the sympathetic activates everything and the parasympathetic doesn't turns down everything. That's not true. Okay. And we want to reinforce terminology. We want to make sure that we can do the terminology successfully. You ready? So first thing is, with the autonomic nervous system, be very critical of your understanding of vocabulary with it. People do really poorly on simple questions because they don't understand the words that I'm using. I don't know the other words to use, so I'm going to use these. Ready? So first, check your understanding of the autonomic nervous system. When I say autonomic nervous system, am I talking about afferent or efferent? I'm talking about efferent. Am I talking about CNS or PNS? I'm talking about PNS. Voluntary or involuntary? Involuntary. Okay. And of course, there are two divisions of the autonomic nervous system, and they are sympathetic and parasympathetic. Exactly. And just to reinforce the involuntary nature, it doesn't hook up to the cerebral cortex. It's primarily in control, or the hypothalamus, the pons, and the medulla oblongata. Older portions than consciousness are in control of the autonomic nervous system. Okay, so here's what we're going to do. We're going to do a little tour. This is not meant to be comprehensive of all of the functionality of the autonomic nervous system, but it is meant to give you good predictive capacity for the next one that you run into. So we are going to go through multiple organs, and each one there is a tissue that we are going to try to control, but there are only 3 choices of tissues for the autonomic nervous system. What are they? Cardiac muscle, smooth muscle, and glands. Got it? So it has to be at least one of those each time. Then we're going to look at the sympathetic nervous system and what it does to that particular situation, and then try to understand it, and whether it represents excitation or inhibition, and then the parasympathetic nervous system for each one. You ready? So we're going to start with the eye, okay? Specifically, what we're going to do is try to control the diameter of the pupil. So which of the 3 tissues will allow you to do that? Smooth muscle, okay? So before we go any further, and I teach you enough anatomy so that you can figure out whether it's excitation or inhibition, somebody explain why it would be worth it to spend a little ATP on pupil dilation during sympathetic stimulation. Why? Explain. Why is it worth it? Go ahead.
It allows more light to come in,
Yeah.
more information.
Yes, exactly. So if a tiger's coming at you, he's got one little chink in his tiger armor, right? You can stick your finger in it right before you die, right? Okay, that makes sense? So you have to be able to take in as much visual information as possible. And it also happens, interestingly, it's not always negative stress. Like being in front of someone you're super attracted to, your pupils dilate like crazy. It's really interesting, right? My little boy is 11. For some reason, he's in that stage where like a bunch of the little girls have crushes on him. So funny. And
So
one
you
of them,
told them
huh?
You told them their eyes dilate.
Oh yeah, and she comes up and she goes, are my pupils dilating? I think my pupils dilate every single time I get around your son. I'm like, this is awkward. Like, why are you telling me? He's like, she told you again, didn't she? It's like, yep. So here's how pupil dilation works, okay? So you got a whole pupil, right? You got smooth muscle fibers that are arranged kind of like the petals of the flower. This is an oversimplification, but it's close enough, okay? This is kind of an origin, this is kind of an insertion, okay? So how do I get that bigger? Do I stimulate these and contract them? Or do I inhibit them and relax them? Stimulate them, right, and contract them. So that means that the tissue here is going to be smooth muscle, and the sympathetic nervous system dilates the pupil, which represents excitation or inhibition. Excitation. And the parasympathetic constricts the pupil, constricts it back down, usually back down to normal. Okay, and that represents inhibition. Okay, so let's go to the next one. The next one is the salivary gland. What kind of tissue? Gland. Okay, so the sympathetic nervous system decreases secretion. I know you understand it, but I want you to put words to it. Why would the sympathetic nervous system decrease salivary gland secretion? Right. If I eat an egg muffin and the tiger eats me, he can digest my damn egg muffin for himself, right? So you do not need to work on carbohydrate breakdown for him, right? So salivary gland secretion stops, and that represents excitation or inhibition. It represents inhibition. This also kind of blows when you get into situations in which your sympathetic nervous system turns on and you need to talk. Bad job, interview, right? You're like, oh, this is going so poorly, and then you're like, I have this weird mouth thing going on. I don't know what's going on. Okay, so that represents an inhibition. The parasympathetic nervous system increases salivary gland secretion, both because it does the antagonistic action to the sympathetic, and also because that's hard to feed or breathe, right? Okay, all right. The lungs, specifically not the lungs themselves, but the bronchioles leading to the lungs, right? So we want to control the diameter of the bronchiole. What's the tissue? Smooth muscle. But you need to understand the anatomy is different than this, okay? The smooth muscle controlling the diameter of the bronchioles is circular. Okay, so how do I get the bronchioles to dilate? Do I excite and contract or inhibit and relax? Inhibit and relax. Yeah? That makes sense? So you inhibit and relax, and it opens up the bronchioles to let more air in. And then the parasympathetic nervous system constricts it back down to normal. Now, interestingly, sometimes people ask, what about allergy situations? When you get asthma and your bronchioles, for instance, dilate because of asthmatic stimulation. Well, allergies are usually not nervous, but what? So I'll give you some choices. Is it hormonal? Is it nervous? What's the other kind of chemical messenger that you always forget? Paracrine. Yeah, it's paracrine stimulation that causes it, right? Okay. So, heart. I bet you can figure out the tissue. Oh, you better say it prouder than that. Cardiac muscle. Okay, and the sympathetic increases heart rate for obvious reasons, right? You got crap to do as a tiger around, and that represents excitation. And the parasympathetic decreases the rate, and that represents inhibition. Okay, stomach and intestines, and then we'll get to the two that are a little confusing for people. Stomach and intestines are doing two things related to this story. They're wiggling and squirting. Got two tissues. What are they? Not skeletal.
Well, if you're the, you get landmark.
Yeah, no, but just in the stomach and intestines. We've got smooth muscle and glands. Good. Smooth muscle and glands. Okay. So the sympathetic nervous system decreases both motility and secretion, right? Turns your guts off. Okay? And that represents excitation or inhibition. Inhibition. And that's an expensive process, and so you basically turn it off. So if you've ever like almost died on I-15, right? You like almost died in a car accident, but then you didn't. Your guts completely turn off, okay? But then as soon as your parasympathetic nervous system knows you're okay, it's going to turn them all back on. And you better be close to a bathroom because you might crap yourself, okay? All on at one time, right? So, so you're fine until your parasympathetic nervous system turns back on. The parasympathetic nervous system increases both motility and secretion, and that represents excitation. Okay, so these next two are the two where you can get confused, so make sure you're paying attention if you were not before. Okay, so these two are two different kinds or categories of arteries and arterioles. So arteries and arterioles are, of course, controlling blood flow to places, right? But do you always need the same proportion of blood to go to all of your organs? Of course you don't, right? Okay. And in the resource allocation story, blood is a resource, right? And so we have to figure out where we are going to send it under different situations. So we have two sets of arteries, and these are not the only ones that fit into these categories, but they're kind of good examples of the extremes. You have arteries that are supplying your skin and your viscera, meaning your abdominopelvic organs primarily, right? Digestive, urinary, reproductive organs, okay? But this time we're not worrying about contracting them, we're worrying about giving blood flow to them, okay? So you got blood supplying your skin and your viscera, and then we've got blood arteries supplying your skeletal muscles, okay? So in either situation, it is going to be what tissue that's going to control the diameter of the blood vessels? Smooth muscle. And the smooth muscle, by the way, is arranged anatomically the same way, right? It's arranged this way. Circular smooth muscle around arteries and arterioles. Okay, so this can be a little confusing. So the sympathetic nervous system should do what to the blood flow to the skin and the viscera? Increase or decrease? Decrease, yes. And how would you do that? Would you excite and constrict? Or yes, you would excite and constrict. Okay, so the net effect of that, guys, would be sympathetic nervous system turns on. Tiger walks in the room. Sympathetic nervous system turns on. White as a freaking sheet, right? Shut down blood flow to my guts. Okay? That makes sense? Okay. The net effect of that, because you've got so much skin, tends to bump up your blood pressure, but then your heart turns on too, so that's going to bump up your blood pressure as well, right? Okay? But it does not want to do that everywhere. You certainly do not want to vasoconstrict and decrease blood flow to your skeletal muscles. You want to do what to the blood flow to your skeletal muscles? You want to increase the blood flow to your skeletal muscles. So what you would do with skeletal muscles is release the same neurotransmitter at a different location. Yeah? Same neurotransmitter is going to be released only at this location. That neurotransmitter is going to excite or inhibit the tissue. Inhibit. And the more you inhibit it, the more dilation you get. Yes? That makes sense? Okay. Now, this totally sounds counterintuitive, but of course it reinforces exactly what I was talking about. Because it's not the neurotransmitter that causes the effect, it is the what? Receptor. So obviously, the smooth muscle in the walls of your skeletal muscle arterioles, yes, is different than the smooth muscle in the walls of your skin, right? Arterioles, right? They have different receptors. Does that make sense? Okay. And little tidbit, there's no parasympathetic innervation of any of your blood vessels, smooth muscles. So here is what I do with smooth muscles. I either increase sympathetic stimulation or decrease sympathetic stimulation. If I increase sympathetic stimulation to the blood vessels leading to my skin, it decreases blood flow to my skin. Yeah? If I decrease sympathetic stimulation like I'm not stressed out, it increases blood flow to my skin. Yes? But now let's think about my skeletal muscle. My rectus femoris, ready? Okay. Tiger walks into the room. Increase sympathetic stimulation everywhere, right? And what it does is it opens up the arteriole leading to my rectus femoris. Get more stressed out, open it up more. Doesn't really start to close down until I stop stimulating the sympathetic nervous system so much, right? There's no parasympathetic innervation. It's just different degrees of sympathetic innervation. Okay? Okay, so last one is the adrenal medulla again. So let's go back and talk about the adrenal medulla one more time. And then I will ask you guys some more questions. Okay, ready? So the adrenal medulla that we saw is our friend that is really the crossover between the nervous system stress response and the hormonal stress response. Okay, so Tiger walks into the room. We can't get out the damn doors, right? We're all about to be screwed. It's going to take us more than a couple of minutes before we're ready to lay down and get killed by the tiger. We are going to have to release a lot of norepinephrine. We need our heart rate to stay up. We need blood flow to our skeletal muscles as long as possible. We could theoretically do that exclusively by repeatedly stimulating the sympathetic nervous system neurons, but that's energetically expensive. What is cheaper, if you need to enhance and prolong the fight or flight response, is to, when you get super duper freaked out, not just a little bit freaked out, instead of just releasing neurotransmitters at the effectors, you also release the epinephrine as a hormone into your bloodstream. And then it will circulate to your heart. It will circulate to your skeletal muscles. It will circulate all over the place, right? Does that sound more energetically expensive than releasing it repeatedly as a neurotransmitter? Right, you dump it into your bloodstream, right? And you've felt that before. I know you have. Have you ever gotten so damn freaked out that somebody asks you to calm down? There's like no possibility in hell that you're going to calm down. Like when you almost die, right? You're like, woo, I almost died. Go ahead.
So is it using the same receptors that this pathway is using too? It's just stimulating with the hormones?
Yeah, and since these are PNS and not in the CNS, we don't have to worry about the blood-brain barrier. It interacts with almost the same category of receptors. I say almost because epi has some that it interacts with and norepi has some that it interacts with, but mostly they're the same categories. So yes, it gets to the same location by a different route, right? And it enhances and prolongs the fight or flight response, right? So you have experienced this, right? You've gotten super pissed off, super freaked out, super scared, whatever you have, and then your heart rate doesn't slow down immediately. Or if you're a parent, it matters to know this, because if you let your kids get into full-blown flip-out mode for whatever the hell thing that they're worried about, like you didn't put the fork in the wrong place, or I didn't get to scan the thing at the grocery store. Somebody almost called Child Protective Services on us one time because Gavin, who is now 18, he was 3 at the time, was super, super intent on making sure that he got to scan everything at the U-scan, and I accidentally scanned something for him. The child was flipping the hell out so badly that my husband had to try to pick him up and shove him in the car, and they're like, do I need to call CPS? He's like, no, it was like a U-scan. It's fine. So he was so freaked out that would it have helped if I just like yelled and said, Gavin, settle down? No. You just need to get him in some isolated place so he can freak the hell out on his own. Or you've probably experienced it. Have you ever like been super primed for an argument with your significant other? Have you ever been super primed? Like you're so ready, like you've got your spreadsheet out, you got your points all in there. You're like ready for whatever their logical fallacies are. You're like, oh no, don't you straw man me, man. So you got them all ready. And then you go up, I have spreadsheets. So then you go up and you say, Mike, I'm really mad about this thing that you did this time because I felt this way about it, and blah, 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 blah. And he goes, Mel, you're totally right. I'm really, really sorry. But I've already got adrenaline coursing through my veins. So I'm like, I like your tone, man. So we just keep going, right? That was adrenaline, not intellect, that made that happen. So yes, once it gets into your system, you have to like let it clear out of your system. And it actually clears through target cells, liver, and kidney, and it takes a little while for it to clear out. Okay, so that's the adrenal medulla. So I want to talk about a couple of things. I want to give you guys a few more questions. And then I want to talk about polygraph tests. Okay? So let's talk about polygraph tests real quick. So a polygraph test is based on the sympathetic nervous system response. And with polygraph tests, you know what they are, right? Lie detector tests. So has anybody ever taken one? I totally want to take one, but I haven't killed anybody. So what they are going to do is they're going to detect some things that are both directly and peripherally related to sympathetic nervous system response. Galvanic skin response, you tend to heat up your body and then you sweat a little bit more. Pupil dilation, right? Heart rate increase. Respiratory increase isn't directly related, but usually comes with sympathetic nervous system response. And now they have these little pads that you sit on that actually test how much your anal sphincter closes up. They do. It's like testing your anal sphincter. I just sit in there and squeeze all the time. Like, how can you tell if I'm lying? But it depends on you being stressed by being dishonest in social interactions. So if that elicits a sympathetic nervous system response from you, it can be detectable. And it can be detectable in ways that if you have a really good polygraph examiner, it can be a pretty reliable response. But I think, last time I checked, it's only admissible in court in 3 states in the United States, and Utah's not one of them. However, it is really used very commonly to exclude people of interest, right? If they think you might have killed her and you're willing to take a polygraph and it's like obvious that you didn't kill her, then maybe they're not going to bug you anymore. I want to take one. I know I'd get caught. Go ahead.
So then how do people beat it?
Let's talk about that. So what it will do is your polygraph examiner will have you wired up and they'll give you a series of questions that should not elicit a sympathetic nervous system response while acknowledging that in the situation you'll have a sympathetic nervous system response, but it'll be baseline, right? So then you ask what you had for breakfast and what your middle name is and all that kind of stuff, and then they ask, did you see her last Thursday? Do you know her, right? And when you get to things that are related to cutting her up and putting her in the trunk, right, you get spikes that are dependable based on that subject, right? Does that make sense? So when the spikes are dependable based on that subject, the best that they can say here in Utah is you can't be excluded as a suspect. Does that make sense? But they can't admit any of it in court here. And it's challenged in the 3 states that it's used in. It almost never lasts in court. But anyway, so in other countries they use it. So a couple of different ways that you could actually beat a lie detector test. Biofeedback works really well. If you know that you're going to have this heart response, what you can do is train your cerebral cortex to override the hypothalamic response and slow down your heart again. It's hard to control pupil dilation, which is one of the reasons that they added it back in. But CIA agents get trained in this kind of stuff. Or you could be like Ted Bundy. Ted Bundy had 3 lie detector tests before he actually finally got incarcerated for killing all of those people. And he started out here in Utah, at the University of Utah. So what did he have that made him fly past these things with flying colors? Yeah, he was a sociopath. So he didn't really have that social interaction expectation that says when I lie to you, I actually feel kind of this social stress of lying to you. He was a sociopath, and it didn't make any difference to him. By the way, so not all sociopaths are violent. Some of them are like CEOs and like maybe presidents even. You know, maybe. So they're not all violent, but they do not have that nonverbal expectation of the interactions with other people. Okay, that's it.
Also,
Yes, sir.
you could, if you like sneak in like a pack, you can like.
Oh yeah, I've heard that too.
If you like, team will elicit a response too. So like, you bring a pack in your shoe,
and then it'll just.
And it'll just like your baseline just away.
Right, so they won't be able to assume anything about the truth.
Yeah. Your
Yeah.
response